In July 2023, I interviewed a company called Terra Circuits at Semicon West. They were a startup that had found two unique applications for the mass transfer of devices onto PCBs or hermetic packages. 2 years on, the proprietary material at the center of this technology is being released. It's called TerraFilm. I'll be talking to Wayne Rickert, the president and CEO of Terra Circuits, after this.
Welcome to Tech Talk with Trevor Galbraith, a video podcast that features industry leaders and experts from the electronics manufacturing community. Recorded at major events around the world and from the studios of Global SMT TV. Now here is your host, Trevor Galbraith.
And welcome, Wayne. Nice to see you. Thank you for joining us today.
Yes, thank you, Trevor. Great to catch up.
Okay. So for the benefit of those that are not familiar with your LIFT process, as I believe the acronym is called, can you briefly explain to us or to our audience exactly how it works?
Sure. LIFT is an acronym that stands for Laser Induced Forward Transfer. And the concept is to use a laser to initiate the transfer of a component from a hard carrier onto a substrate or a surface. Originally, it was thought of as a way to transfer, literally transfer metal from a metal plate onto something that you wanted to etch. But today, we're using it as a way to hold hundreds of components directly from a singulated wafer on a hard carrier, and then use a laser to target the components we want to release. And by doing that, we can transfer components that are very, very small or very thin and fragile. And we can overcome some of the deficiencies with pick and place.
Great. Well, we've got a little video that actually gives an animation that shows something of how this works. Maybe you can talk us through what's happening here. I'll just run the video now.
Sure. So here you see a micro LED on the left. You see RGB, red, green, and blue micro LEDs about the size of a dust particle. And this is the process where an excimer laser is projecting a beam through a mask, and then that is activating a material like TerraFilm, which is holding these micro LEDs. And when it's activated, it sublimates into a gas, provides a downward placement force, and you can see the components are transferred en masse onto the substrate.
Right. Okay. So it's really quite a novel process. But I mean, you can literally get thousands. It can pick up thousands of LEDs in one take, which is much faster than any pick and place machine will ever be able to do it. That's for sure. So what developments have you had in the process since we last spoke? I mean, we spoke 2 years ago now. So what has happened since then?
Well, since then, the main development, I think, from our standpoint, is we were initially transferring dummy die in our lab. They were about 40 by 50 microns in size. So very, very small when you consider that the diameter of a human hair is about 200 microns. Mm-hmm. They were very small, but still quite a bit larger than a micro LED. Since then, we've been able to transfer actual micro LEDs that are 9 microns in size. So to put that in perspective, you're talking about something that's smaller than a red blood cell. And we can transfer those now en masse with a high degree of accuracy. Another development is we have been working with two of the largest micro LED display manufacturers in the world on their processes to actually get this into production. So at this point, we're not in production yet. It's still at the evaluation stage. Transferring something that small is very difficult, and there's still some technical problems with micro LEDs themselves to overcome to get high yield at that size of a component. But we're making steady progress, and we're working with all the right players.
Great. So how far do you think you are from actually having production models running?
Yeah, I think this is in terms of manufacturing at consumer readiness scale, we're probably looking at 2029 to 2030. So it's still a ways away. The material itself and the process is mature today. What we don't have is a production tool that's ready to deploy. And as I said, there's one of the other barriers for micro LEDs, at least, is that micro LEDs themselves still have a ways to go to be able to yield at high volume. So this is a manufacturing challenge for the micro LED manufacturers. We can do it today with the components that are larger on the 30 to 40 micron scale. But the real sweet spot for the industry is to get those very tiny, below 10 micron components to transfer. At that point, you can start talking about being commercially competitive with OLED.
Right, right, okay. So is the material itself manufactured by Terra Circuits? Is that the TerraFilm material? Is that
It is,
manufactured?
yes.
It is, okay.
Yes, it's a proprietary formulation. We manufacture it ourselves. We do have about half a dozen scale-up partners that we've identified high interest in the material from the semiconductor, chemical, and material industry. So we anticipate that at the point that we're ready to scale up, that one of those go-to-market partners will actually be doing under license some of our manufacturing for us.
Right, okay, excellent, excellent. Okay, well, the beauty of that material, as I recall, was that not just its temporary bonding capabilities, but the fact that when you do apply the laser to it, it literally vaporizes without leaving any deposition or contamination on the board. Is that correct?
That's right. In fact, that particular advantage is something that's finding a lot of interest in other sectors besides micro LED transfers. For example, we're moving from a world where we've gone from wire bonding to increasingly small solder balls to thermocompression bonding, and now the buzz is all around hybrid bonding, which requires a very pristine and clean surface. It turns out that the temporary bonding materials that are being used today on wafer-to-wafer transfers, they leave quite a bit of residue that has to be removed with a solvent. And the introduction of the solvent interferes with the material characteristics you want for hybrid bonding. Right. So TerraFilm is starting to attract interest from the hybrid bonding community as a way to protect and temporarily bond components prior to that final hybrid bonding step.
Right, right. Well, that's interesting because that brings us on to the wafer side of the business, because that's the other application you've got. Is the one side is doing the LED process, but the other side is being able to lift small chiplets and put them in place accurately at one time. Can you talk to us a little bit about that? And while you're talking to us, maybe, in fact, I think I've got a second clip which shows it literally lifting the devices off of the wafer, and I'll run that at the same time.
Sure. So when we talk about chiplets and components that are that size, here you see an example. It's kind of what we would be doing with chiplets. This is still a display application, but what we're doing here is we're transferring red, green, and blue micro LEDs, and we're doing a pitch conversion at the same time. So they're being fabricated at one pitch, but then they're being laid out on the substrate at a different pitch, and you're building a pixel of one red, one green, and one blue, and that is a way to build a complete, fully functional display. Right. So when you think about building an assembly that uses multiple chiplets, using this process, you could lay out all of the components of a similar type, and you could lay them out in such a way that you're doing parallel assembly of whatever it is you're building. So you'd lay out the first chiplet, and then you'd maybe a dozen or 2 dozen or a couple hundred, depending on the size of the module you're building. And then you'd lay out the second chiplet and the third chiplet, and you get the same advantage of parallelization that you get from deploying micro LEDs. But in this case, you're building some type of assembly. It could be a 5G, 6G assembly, or it could be a it could be an IoT assembly. Anything that uses triplets could benefit from that.
Right, right, yeah. So it's a remarkable system. One question I've got is that the demonstration I've seen used so far has been using a laser source from Coherent. Is this process restricted to only specialized lasers from Coherent, or can any laser company be used?
So the material itself is activated at a particular wavelength. So Coherent makes they make a laser that's a coherent laser that is certainly one that can generate the right appropriate wavelength for us, which is 266 nanometers. We can also use a diode pump laser, which is a lower cost laser that has some different characteristics at 248 nanometers. So that's another possibility. We're looking at different formulations that can use higher and lower wavelengths as well. So there's a broad range of laser technologies that will work with our material. Coherent is someone that's far along in making a tool that, into Coherent's place, they've targeted micro LEDs, so they can do several steps in the micro LED panel fabrication process. But there's other companies as well that have laser-based tools like 3D Micromac, KNS, Toray and Shinetsu from Japan both have laser-based tools. So we see the interest in this approach really ramping up in the tool manufacturers, including Applied Materials is looking at entering this market as well. So a lot of interest from the established players. I think that it's pretty clear the advantages in both throughput and accuracy are unachievable with a purely mechanical means. And this is something to keep our eye on the tool side. It's going to be an area that really expands.
Right. So really that is the bottleneck at the moment, is that we need the tooling to make it work. The process has been proven and is working, but we need the tooling in place to be able to make, offer something that can go into mass production essentially.
Right, that's correct for the micro LEDs for sure, and also for any type of parallel assembly. I think in the other application we talked about, which is hybrid bonding and temporary bonding and debonding of wafers, the tools that exist today that are used for laser debond will work with our material. So, and another interesting aspect of our material is that if you're not so concerned about the high speed transfer that's required for micro LEDs, we can also activate and do that clean decomposition with just heat, without actually using the actual wavelength. And then you still get a heat-driven clean decomposition. So the materials found application in that space as well, using existing tools.
Right. Okay. So, I mean, do you envisage any other applications coming down the pipe beyond those that we've already seen?
The one that's really interesting is the material has a unique characteristic in that you can selectively decompose it using as I said, heat and light. Today we use a mask for that, but Heidelberg Instruments was able to demonstrate that they can actually decompose the material using one of their tools, both in the X, Y, and Z dimension. So in that case, you could use it as effectively a dry developable photoresist for maskless lithography. So something like E-beam or a hot thermal tip could selectively decompose the material. It has certain advantages in that, in theory, if you don't require a wet development, you might be able to avoid some of the challenges with lithography, with direct write lithography that use a developer, and then the developer, through capillary action, can cause feature collapse. So in theory, we should be able to avoid that problem. So that's an area we're just starting to investigate with one or two partners.
Wow, that's fascinating. So we'll certainly keep our eyes open on that one. So tell me, what are the next steps? I know you're working very hard in the lab, and we've seen some nice pictures coming through from your lab here. But what are the next steps in the evolution of the process?
Well, we continue to bring on development partners that are looking at these different scenarios. As you can see in the lab, we've actually built our own laser transfer tool. We've become quite adept at understanding how to put together the laser systems and the optics to build a tool. So we continue to work with tool partners to get to that next step where there's a production-ready tool that's available in the market. We continue to explore the semiconductor applications as well. So between temporary bonding and debonding and chiplets, there's lots of opportunities there. And I think as people recognize that we have a need for a very clean type of decomposable temporary bonding material, that's an area where we're getting a lot of interest, and I think it's an area where we have competitive advantage over some of the other temporary bond debond materials that are out there in the market today.
Right, excellent. Okay, well, it looks like you're on the right track, Wayne. And of course, I know the rest of you. I met the rest of your team a couple of years ago. Dr. Jana Sheets and of course Joe Felstad's on your board as well. So lots of good technology, good people behind you. So I wish you every success with it, and look forward to getting another update. Maybe next time at Semicon West in next September in Phoenix.
Yes.
So we'll look forward to that. But anyway, for now, I want to thank you for coming in and sharing the information today, and we'll look forward to catching up in the future.
Very good. Thank you so much, Trevor.
Okay, thank you, and thank you for watching.